Okay, hi everyone. This is going to be the last of the 3 lessons I'm filming today, so as happened last week, I'm probably going to be a bit worn down for this one. Sorry if I lose track of my words at times. Anyway, this one's going to be on DC motors. It's going to be pretty much carrying straight over from what we were doing last time, which was about the forces on current carrying wires due to magnetic fields. This is going to be a direct application of that. So those ideas are what we're going to use today in order to understand how DC motors work. Now, first of all, there are 2 things in that title, motors, which is obvious, I guess, but we're going to talk about DC motors. They use DC current. You can get AC motors. We don't look at those in year 12. They have a lot of different parts to them. They're more complex in design. DC motors tend to be a bit more simple, and they're what we focus on. So remember that DC current means the current is flowing around constantly in the same direction, or our positive and negative here, we've got a motor setup, they're not going to change. So we're going to talk about current changing direction later on, and that's going to be due to this sort of setup. We've got our DC battery. There's current constantly coming out of here and current constantly coming into there. That's just what it means for something to be DC. Now, the 2 main components of a DC motor are a magnet to produce a magnetic field and a current carrying wire. So we've got our magnetic field, our north pole and our south pole. Like I said, when we looked at magnetic fields, there aren't any magnetic monopoles, so it's not just we've got a north pole sitting there and a south pole there. These might be part of a larger setup. We might have a south pole out here and a north pole out there. We just indicate that this is our setup. We simplify it down, even though there would be more to this than is indicated in this picture. We've got our magnetic field. We've got our lines showing the direction of the field running from north to south, as shown by these arrows. And we've got our current carrying wire in the middle. It's a loop that has a square or rectangular shape to it. This is the typical shape that we look at when we do stuff on motors. We have some kind of rectangular shape, and I'm going to be using this loop today just as a kind of indicative, well, standard sort of shape for a loop within a magnetic field in a motor. That's what this is going to look like. So we've got our current carrying wire. It's getting its current from the battery or power source out here. So the power flows through here around the loop. It flows through this thing called a commutator. It's going to be a very important part of the motor that we look at later on, but we're going to leave it to the side for a moment and focus on the other parts, the main things you can see here. Current flowing around that loop through there. So those are our 2 parts, our thing producing the field and our loops that are going to experience a force because they're carrying a current and because they are within a magnetic field. Now, before we get on to that, we need to talk about a physics idea that's called torque. And a torque is a rotational force. It occurs when a force causes an object to rotate. Most forces that you've looked at as part of physics are called translational forces. You push on something and its center of mass, which is normally stationary for torque questions, but not always, it's going to move. So if I push on a table and I push it across the room, then that's just going to be a translational force. It's moving from one point to another. If I was to just push on this TV and cause it to rotate in its circle, it's not really going from one point to another. It's just rotating around. That's going to be due to a rotational force due to a torque. Now, the equation for torque is going to be, we use tau, this little T-looking thing, to indicate torque. It's equal to RF sine theta. Now, I'm going to use my example down here and when I talk about what things are. So this is like a door. It's even got a handle, so it's definitely a door. You push on the door out here, and it's going to swing around. It's one of those doors like these classrooms have. So it's got some hinges here. It's going to move around the hinges. You push on it at this location, the door moves around. R is going to be the distance from where the force is applied to the axis that it's rotating around. We call it the moment arm, as you can see on there. I'll be using that notation, that kind of vocabulary, jargon later on. So, weird sound, I think it's the train. So we've got our moment arm, our value for R. We've got the force, the F, which is how hard I'm pushing the door with. And we've also got the angle between the force and the moment arm. So our moment arm is along here. Our force is on there. in this particular example, you can see the angle between them is going to be 90 degrees. So in my equation, I have sine 90 degrees. That's just going to be a value of 1. So when I'm pushing on this at an angle of 90 degrees to the moment arm, I get the maximum torque that I can get. This value basically doesn't matter to my calculations when I've got a 90 degree angle between the force and the moment arm. If I decrease that angle by taking it out here, so the angle is maybe like 20 degrees now, or I moved it in the other way so that it was in 20 degrees at that angle, well, I guess out here it would be more like, 160 or something. But as I change my angle from 90 degrees, move it out either way, this term, the sine theta, is going to become less. As a result, I'm going to get less torque, less rotational force on the door. I can also decrease the torque by moving in and pushing closer to the hinges, but that's not going to matter so much for today's stuff. Normally what matters is just the angle between the force and the moment arm. But yeah, if I decrease the moment arm, then the torque becomes less. If I take my angle and I was to decrease it to 0 degrees or increase it to 180 degrees, at those 2 points, I've got sine of 0 or sine of 180, depending on which way I go. That's going to get me a value of 0. So I'm going to have 0 torque when I'm pushing towards the moment arm or pulling away from the moment arm. You can imagine that if you've got your door and you're trying to push, like if the door's open and you're trying to push on the edge of the door towards the hinges, it's not going to rotate. There's going to be no rotational force on it. So just keep that in mind when we're talking about motors. We're going to be looking at something that's rotating. We're going to be thinking about the torques that are acting on the different sides of the rotating loop. Now, I've got a loop up here. This is straight from your textbook, so if you can't see it very clearly, I'm putting these PowerPoints on Compass, so you can see them on there, or just use your textbook. We've got a loop. It's in a magnetic field. It's got a current flowing around this way. It's got sides A, B, C, and D. On side A, there's an arrow showing that the force on that side, due to the magnetic force of the magnetic field on the current carrying wire, that force, things haven't gone weird, have they? Whatever. That force is going to be directed downwards. If we used our right hand slap rule, we could see that magnetic field lines pointing to the right, current is pointing inwards. So the force is going to be down. That's the direction of the force on this side of the loop. The force on side DC is going to be pointing upwards. We could use our right hand slap rule and figure out that the magnetic force on that side is up. On sides BC and AD, you can see that the current is either running parallel to the magnetic field lines or what we call anti-parallel, where they're parallel to each other but in opposite directions for side AD. Because they're parallel to each other, and because we had that sine term in the force on the current carrying wire last lesson, the force on those two sides is going to be 0 at these points. So there's a downward force on this, an upward force on this, 0 forces on these two sides. As a result, this side moves down, that side moves up, the whole loop is going to rotate upwards as a result of those two forces. So as it rotates, we get to position B. Now we've still got a downwards force on side AB. We've still got an upwards force on side CD. Those two forces are going to cause the wire to continue to rotate. On side AD is no longer completely parallel to the magnetic field. Now there's some angle between the magnetic field lines that's not 0 or 180 degrees and the direction of the current. So there's going to be a force on side AD and there's going to be a force on side BC. The force on side AD is going to pull outwards. The force on side BC is going to pull outwards in the opposite direction. Those two forces are going to sort of pull out on the wire, but they're not going to affect its rotation. So when we're looking at the rotation of a loop of wire, we almost always focus on this side and that side, the one that's getting pushed down and the one that's getting pulled up, because those are the two sides where the forces are causing the rotation. There are forces on the other sides. They cause the loop to either pull out slightly or, I guess in this case down here, push in slightly, but they're not going to affect the rotations. You need to know those forces can be there, but they're not the forces that drive the rotation of the loop. So the loop rotates. It rotates until it gets to this vertical position. Now, when it's at that point, the force on this side is up, force on that side is down, outwards and outwards. The loop is basically just going to stay there. The forces are going to push it up and pull it down. Those forces are going to cause it to be in a stationary position. If we reverse the direction of the current, so you can see it was going around this direction at this location. If we reverse the direction of the current, the forces are going to all change direction. We change the direction of the current, we change the direction of our forces. They've all gone from outwards to inwards down there. Now, I've got to remember how I was going to set this up. Let's do this. There are two different ways I could have done the next bit, and I'm going to go with what I've got. So if the current only flows through the loop in one direction, the loop won't rotate around smoothly, but will get stuck perpendicular to the magnetic field. So I'll go through this a bit now. If this is my loop, and it's got a current flowing through it, it starts having a current, it's going to rotate, it's going to get to this top position, and it's just going to stick there. Not very good for a motor. We want there to be a smooth, continuous motion or rotation. That's how we want a motor to work. So this represents a problem. We don't want it to just turn half a turn and then stop. We want it to keep going and rotate around continually. And to fix that problem, we're going to use something called a split ring commutator. It's called a split ring because, as you can see in this diagram, it's like a ring that's being split into two halves. This is the thing that back at the start of the lesson, I said that we've got some stuff here that we're going to look at later once we looked at the loop and the magnetic field. And that's what this thing was. It was the split ring commutator, drawn a bit different. It's not so much a ring as so much a little cylinder split in half. But yeah, it's a different way of showing the same thing. Now, the idea is, hopefully this comes through in the video, we've got these grey bits here connected to the wires. So the loop's not shown, but you imagine that these bits coming out are these parts of the loop, and the rest of the loop would be out there. And they're connected up to these semicircles. One side of the loop would be connected up to this one, the other side of the loop connected up to that one. All the grey stuff is going to be rotating as part of the motor. So the loop is going to rotate. These parts of the commutator, the split rings, are going to be rotating as well. These little brown, greyish bits or darker grey out there, we call those brushes. They're going to be in contact with the commutator. So the grey parts here in the middle are going to rotate. These brushes are going to stay in a fixed position. Now, that's going to be useful for getting the motor running the way we want it to. Because what the split ring commutator does is that it causes the current in the loop to change direction every half turn. Now, like I said before, these are DC motors, which means that we've got a DC power source out here. The current flows out of that power source in a constant direction. It's always coming out this side and then coming in that side. What the commutator does, though, is it switches the direction of the current in the loop. So even though this current is constant in the same direction, because these contacts are rotating, our currents through the loop is going to switch directions. So I'll just go through these points before trying to explain that in more detail. When you change the direction of the current through this loop, well, if the current is moving through in this direction and the force was up, if we switch the direction of the current, then the force is going to suddenly be down. We switch the direction of the current, we switch the direction of the forces on the sides. And through this sort of action, that's going to enable the loop to keep rotating in the same direction. The thing we want it to keep rotating around smoothly in one direction. That's going to be allowed because of this split ring commutator. So I've got my loop here, and like I said, these split rings are going to be rotating as well. Normally they rotate, sometimes they don't, but it's easy to understand if you think of them as rotating too. So let's say we've got our loop, it's got this little, hopefully it comes across, little sticker on it, a little bit of orange and white. Now let's just say we've got our loop here and it's rotating around and it's connected up to the red side of this. Now, if this rotates around to, say, here, and it's not coming through perfectly, but I'll make do. What's going to happen is that this side is now going to be connected to this side of the circuit. It's going to be connected to the little green brush that's hidden behind there. And as a result, the current is going to be coming in through here and going out through here. So previously when this red bit was connected up to this red brush, the current comes in through the red brush, goes in through the red ring, goes around this way. Now that this has rotated around, the red part of the ring would be connected to the green brush, the green part of the ring connected to the red brush, so the current goes in through the green bit, comes out through the red bit. Even though it's coming through the same direction out here, it's going into this part, it's coming out of this part. The current has switched direction because these two rings have switched which brush they're in contact with. So that's the purpose of the commutator. It allows the current within the loop to change direction at set times. That changes the direction of the forces on the sides of the loop in a way that's going to allow it to keep rotating. Now, give an example. So, big magnetic field pointing to the right, and let's just say that our loop starts out here. It starts out perpendicular to the magnetic field. That's going to be the optimal starting position. Now, because it's this and that side are perpendicular to the magnetic field, these sides are always going to be perpendicular to the magnetic field. They're always going to have a force on them. It's just a question of whether that force causes the sides to rotate, because if you remember stuff on torque, depending on where your thing is located in the field and which direction the forces are in, that's going to affect whether the forces on the sides actually cause a torque, whether they actually cause a rotation, because at some orientations, the forces are going to cause it to rotate because of where the forces are directed. At other orientations, the forces won't cause any kind of... Am I stuffing this up? Hold on. I think I'm stuffing up in terms of the best optimal... Yeah, I'll start it out here rather than the way I had it before. Sorry. At some positions, like here, for example, the force is going to cause it to rotate. If it was in this position, for example, the force on, say, this top bit of wire, easy for me to touch, the force on that isn't going to cause a torque. It's not going to cause a rotational force. So this is why I introduced the idea of torque, because there's always going to be a force on this top side and there's always going to be a force on this bottom side. Those forces aren't actually going to vary in magnitude as the loop rotates. There's always going to be a constant force on this side and a constant force on that side. What is going to vary is the torque on each side, the amount of rotational force, because you can think about this loop as rotating around the center of the loop. Now, when it's like this, there's a distance between here and here, between this side and the center of the loop. When it's at this position, we're actually going to say that there's zero distance between horizontally this loop and this side of the loop and the center of the loop. Rather than thinking about it as rotating around a point, we can think about it as rotating around the plane, and the plane's going to extend up here and there'll be an intersecting and there'll be no distance between them. It's more complicated than it needs to be. You basically just have to say that at one position, the force on this side is this far away from the center, so you get maximum torque, maximum rotational force. At this position, the force on here is at a distance of 0 horizontally from the center of the circle. Because there's a moment arm of 0, there's no torque exerted on the loop by the force on this side. So the torques are going to vary, the forces on this side and that side are going to be constant. All right. Now, with all that said, what happens is that you have your loop, it starts out here, it starts having a current flow through it. That current results in a torque that causes it to rotate. That torque is going to get smaller and smaller as the loop rotates. As I said before, it's going to get to this position and then it's going to want to stop. It's going to want to just sit there and kind of bounce back and forth. If you're setting this up using a commutator and everything the right way, what will happen is that you get your loop rotating. It's got a bit of momentum, so once it gets to the top, you have your loop continue to rotate a bit past where it would otherwise stop. So it goes up, it's got momentum, it keeps going. Now, if the current in the loop stayed in the same direction, say the force on this side was upwards, which it would have to be for this to be going up. If the force on this side was upwards and the current wasn't changing direction, the force on this side would push it back up and it would keep getting pushed up and staying at the top of the loop. What the commutator does is that there's a current going through it. It rotates up to this top point. Because of its momentum, it moves slightly past the top. And at this location, the commutator kicks in. The rings switch which brush they're in contact with. The current through the loop changes direction. So up until now, the force on this side, because of the currents through the loop, it was pointed upwards. Right at this point, the current is going to be suddenly switching direction, and now this force on this side is going to be pointing downwards, and the force on this side has gone from being down, pulling it down, to suddenly pushing it up. So the force on this side is up, now it's down, it keeps rotating around, the commutator switches direction, or switches which brush it's in contact with, the current switches direction through the loop, the forces switch direction, and now this force on this side has gone from being down to being up, and there's this rotation because the current keeps changing direction and the forces keep changing direction as a result, and because it's timed properly and the way it needs to be timed, the forces change direction every half turn. That results in the loop rotating around smoothly. So this is kind of, I've been talking for like an hour now and my voice is starting to run out, but the point is that the commutator just allows the current to switch direction every half turn. This allows the forces to, I think my next slide says that. No, it doesn't. That's surprising. The commutator gets the current to change direction through the loop every half turn. This changes the direction of the forces. This enables the loop to continue rotating in the same direction, which is what you want a motor to do. You want to take some kind of electrical energy as input, as current, and from that electrical energy you want to produce kinetic energy. You want to produce motion. That's what the goal of a motor is. Later on in our next area of study we'll look at generators, which take motion and use them to produce electricity, the reverse process. But motors, you have electrical current going in, you have motion being produced from that. That's what a motor actually does. All right. I think I might have skipped ahead a bit, maybe not. In a motor with only one loop of wire, the torque is at a maximum at some point and at zero at other points, which causes it to move in a sort of jerky motion. Here you got maximum torque, maximum acceleration, and it's going to be at a maximum speed by the time it hits the top. Then it's got less acceleration, so it's going to slow down, it's going to speed up, it's going to slow down. If you're driving your car, you don't want it to be slowing down and speeding up multiple times every second. You want it to be moving at a constant speed. You want the motor to be driving the wheels at a constant rate. So rather than having a single loop of wire in your motor, a real motor is just going to use a lot of loops of wire oriented at different spaces. So if I had my motor, it might have one loop of wire here, another loop of wire here, here, lots of loops of wire, which means that when one loop of wire has a maximum torque, another loop of wire is going to have zero torque, and as they rotate, the amount of torque on each loop of wire will change, but the overall torque on all the loops of wires should remain at a constant value. So because of that, you get a constant torque, constant rotational force, constant rotation. It's not speeding up, it's not slowing down, it's going to work the way that you want it to. So that's just what real motors use. Now, a bit of notation. In a motor, we've got two bits. We've got the static and non-moving part, which is normally the set of magnets in the diagram that I've showed you before. The magnets weren't moving. We called them the stator. So stator, I remember that it corresponds with the word static. Static is in not moving. So all the non-moving parts of a motor, we just collectively call those the stator. The rotating bit, which does move, is referred to as the armature, the loop of wire that I had up before. It's not static, it is moving, so that's the armature. And it's easy to sometimes mix them up in situations such as this one, where sometimes rather than using permanent magnets to create the magnetic field, you actually generate the magnetic field of your motor using what are called stator coils. You produce the magnetic field not using permanent magnets, but by running an electric current through a set of loops of wire. Those loops of wire produce your magnetic field, and then a different set of loops of wire are going to rotate as a result of the forces produced by those magnetic fields. So here in this picture, we've got brushes, we've got shaft, we've got lots of different things, but we've got armature windings, the little loops around in here that are going to be rotating. We've got stator coils, which are these big sets of coils here that are going to produce magnetic fields that exert forces on the armature windings and cause them to rotate. This would be like a basic example of the armature windings. So we can produce magnetic fields in different ways, and check if everything's going good. I've got 25 minutes left, I think. Oh no, I've been talking for that long, Jesus. But just keep that in mind. It's just a bit of notation that we use when we talk about motors and their different parts. Now, this is a bit unfortunate because this is more fun to do on your own. Hopefully there's a bit of time to do this when you come back, but it's still also going to just illustrate what I've been talking about. So here, you're recording, we've got a very basic motor. It's got a magnetic field being generated between the two magnets out on the sides. It's got a set of windings in the middle. You can see that's, where's the thing? There it is. We've just got windings here, loops of wire. You can see that there's a lot of loops and that they're oriented, hopefully you can see, I have no idea. They're oriented in a few different orientations, which just helps produce a constant torque and keeps it rotating at a constant speed, avoids that sort of jerky stopping and starting motion that you get with only one loop of wire. So here we've got our stator, which is going to be due to the magnetic fields of these magnets, and we've got our armature, which is just this rotating part, the loops of wire in the center. So these produce the magnetic force, these carry the current, there's a current on them due to the magnetic force, not a current, there's force on them due to the magnetic field, and that force is going to cause them to rotate around the way you want the motor to. And we can take those magnets off and replace them with a loop of wire, this one here. You can connect it up to an external power supply and run current through here. This is a solenoid, or it might even be an electromagnet if there's a bit of iron in the middle of it. But if I run a current through this, it's going to produce a magnetic field. That magnetic field can basically substitute for the magnetic field of the permanent magnets that I had set up before. So this is now my set of stator coils. They're not rotating, they're just getting a current through them, producing a magnetic field. That magnetic field interacts with the current running through the armature windings down here and causes them to rotate. This produces a magnetic field. That magnetic field exerts a force on the current flowing through the armature. So these often get used. Often when you're talking about a motor, particularly industrial scale ones, you produce your magnetic field using an electromagnet because they're capable of producing much stronger magnetic fields than your simple permanent magnets are. So just keep that in mind, that when you see two sets of coils, one's going to be stationary, the stator coil, one's going to be moving, the armature windings. They serve different functions even though they're both sets of wire that are carrying currents. So that's a lot of talking. I think that's essentially all I need to talk about for this. Now what you're doing is some stuff from chapter 3.2 in your textbook. You're doing some Edroller quiz questions as well. With that motor thing that I just showed you, you actually do get a power pack and connect it up, and it rotates if you set it up right. And it's got a little commutator. I might even show it. It's got a commutator here. No, there's no chance of you seeing that. It's got a split ring commutator, which just enables you to change the direction of the currents through the windings, and it makes it work really nicely, but I can't really show it to you when the iPad doesn't quite give me the degree of resolution I need. Whatever, I'm rambling. So yeah, you're doing the stuff from 3.2, you're jumping over 2.5, which is something I'm going to do in a future lesson, and you should just be getting on with that.